3 days ago, magnetometers across the globe registered something impossible. A spike that shouldn't exist. The timing was perfect, the signature was unmistakable, and the source was beyond comprehension. The Andromeda galaxy, 2.5 million light-years away, somehow reached across the vast, cold void of intergalactic space and rattled our planet's most vital defense, its magnetic shield. If this data holds, it completely reframes where space weather begins. For all of human history, we have thought of our planet as being in a cosmic conversation with only one partner, our sun. We are no longer talking about just solar storms or solar wind. We are now talking about the staggering possibility of intergalactic forces that can reach out and touch the Earth. You are about to hear the theoretical mechanism behind this cosmic connection. You will see the strange, rhythmic fingerprints left in our planet's magnetic field data, and you will understand why, in quiet, secured meetings, scientists are recalculating everything they thought they knew about our world's defenses against the cosmos. But here's what's keeping researchers awake at night. Staring at their screens in the pre-dawn hours, one specific number keeps repeating. A strange resonance appearing across every instrument, on the ground and in orbit, that detected this bizarre event. It is a frequency that matches nothing we have ever seen before in any catalog of known cosmic sources. The timing window of this event suggests that whatever the signal was, it left the Andromeda galaxy at a moment in time when our own Milky Way galaxy was in a very specific and predictable alignment. That's not a coincidence. The data hints at targeting. And if Andromeda, our nearest galactic neighbor, can do this once, what is stopping it from doing it again? The reports first began to trickle in through secure data channels, linking a powerful directional energy transient from Andromeda with a sudden, sharp jump in the magnetic field here on Earth. This jump was short, lasting only seconds, and it happened during what should have been quiet solar hours, a period when our sun was calm and our magnetosphere was stable. But multiple, independent sensors, both on the ground and in orbit, all recorded the exact same anomalous signature within minutes of each other. Ground-based magnetometers from NOAA's global network, from the Arctic to the Antarctic, registered the spike. Far above, the European Space Agency's trio of swarm satellites, designed specifically to monitor the magnetosphere with exquisite precision, caught it. Even ultra-sensitive quantum sensors buried deep underground in shielded research facilities to isolate them from terrestrial noise, they all caught it. The timing of these independent detections lines up within an astonishingly narrow 6-minute window. This is not an instrument error. It's not a local glitch. The data is clear. This was a real, physical event that affected the entire planet. Let me break this down in plain terms. Your magnetosphere is Earth's magnetic bubble. It is an invisible but immensely powerful force field that wraps around our entire planet, generated by the molten iron core deep within. It is our first and last line of defense against the harsh radiation of space. Normally, it responds to only one thing, our sun. The constant stream of charged particles, known as the solar wind, hits it, compressing it on the sun-facing side and stretching it out into a long tail on the night side. Powerful solar storms, coronal mass ejections, can bend it, twist it, and pour energy into it, creating the beautiful auroras at our poles. That's normal. That is the physics we understand.
What is not normal is for this shield to react to something else, something much, much farther away. A transient is a brief flash of energy in space, like a flicker of cosmic lightning. Most of these events happen within our own galaxy, the Milky Way, and we barely notice them. They are too far, their energy too diffuse by the time it reaches us. But the narrow detection window for this new event, the perfect overlap in the detection times from multiple, disparate sensor platforms, suggests that something traveled across 2.5 million light-years of space and still had enough coherent energy, enough structural information to physically rattle our planetary defenses. The pattern being reported echoes a known but incredibly rare cosmic effect that scientists refer to as bell ringing. The most famous precedent for this occurred in 2004, when a magnetar, a type of dead hypermagnetic star in our own galaxy, actually made Earth's magnetic field vibrate like a struck bell. For a terrifying 7.5 seconds, our planet's magnetic field, the very shield that protects all life, pulsed in perfect sync with the rhythmic beat of a dying star 50,000 light-years away. If the data from the Andromeda event is confirmed, we are looking at the exact same phenomenon, but across a distance 50 times greater. This is a leap in scale that is almost impossible to comprehend. So how is this possible? How could a whisper from another galaxy shake our world? 3 new theoretical frameworks have emerged that could explain how this cosmic connection works, and each one is more unsettling than the last. First, there is the resonance trigger hypothesis. This theory posits that even an incredibly weak pulse can ring any system if it hits the perfect resonant frequency. Think of an opera singer shattering a wine glass with her voice. She doesn't need to scream with brute force. She just needs to hit the glass's exact natural vibrational frequency. Earth's magnetosphere, like that wine glass, has its own set of natural frequencies, determined by its size, its shape, and the plasma that fills it. A signal, even one that has traveled for millions of years, if it is tuned to precisely match one of those frequencies, could amplify a tiny, almost imperceptible input into a measurable, significant spike in our sensor data. This wouldn't be an act of brute force. This would be an act of cosmic precision targeting from across the universe. Second, scientists are seriously considering the intergalactic magnetic bridge idea. Galaxies like ours in Andromeda do not simply float in an empty void. They are embedded within a vast, invisible structure known as the cosmic web. This web is made of vast threads or filaments of superheated magnetized plasma that connect distant regions of the universe like cosmic highways. These filaments can act as waveguides, carrying coherent signals across millions of light-years without allowing them to lose their structure and dissipate. A powerful pulse from Andromeda, if properly aligned, could ride one of these magnetic highways. By the time that pulse reaches the end of the filament, near our own galaxy, it would still be focused enough to deliver a concentrated jolt to our sensors. Third, and perhaps most simply, we may just now be noticing a phenomenon that has always been happening. We're living in the quantum-grade sensor era. New magnetometers developed in the last decade, sensors that rely on the bizarre and wonderful properties of atomic physics, can now read magnetic field shifts that older classical instruments would have never caught. We now have atomic sensors, quantum interference devices, and sophisticated artificial intelligence systems that can sift through petabytes of data, flagging tiny anomalies in real time. We are, for the first time in human history, detecting the cosmic whispers that previous generations of scientists couldn't even imagine were there. To keep it simple, think of Earth's magnetic field like a massive, finely tuned drum. Most days our sun plays it, beating out a steady, familiar rhythm. But if a drummer, positioned impossibly far away, were to hit another instrument tuned to the exact same pitch as our drum, the drum skin here would still vibrate in sympathy. That's the core idea here. This isn't about brute force. It's about precision. And what makes this discovery so deeply unsettling is that all three of these possible mechanisms, resonance, magnetic bridges, or the new patterns we are seeing, all suggest that this event was not random. Frequency matching requires targeting. Magnetic bridges require a precise alignment. And the new patterns we are seeing suggest a structure, not a chaos. It implies a system.
The theoretical frameworks are in place. Resonance, cosmic filaments, and quantum-grade sensors could all explain how a signal might cross the immense distance from Andromeda to Earth. But it's the signal itself, the specific pattern hidden within the data, that's truly keeping researchers up at night. A strange, repeating number appears across every single detection system that logged the event. It shows up twice in the raw data stream, once as the signal first hits the outer boundary of our magnetosphere, and then again, moments later, as it resonates down through the magnetic field lines toward Earth's surface. This exact repetition suggests we are not looking at random, chaotic cosmic noise. We are looking at a structured signal, something with a deliberate internal timing. And the frequency itself? It matches absolutely nothing we have ever seen before in any catalog of known cosmic sources. Not a pulsar, not a quasar, nothing. But when scientists traced that strange repeating frequency back to its source direction, what they found could change everything we thought we knew about galactic communication. Here's where the data gets incredibly interesting. We are seeing a short 12-second magnetometer jump, paired with a distinct repeating interval pattern. At the same time, a radio telescope survey, pointing in the general direction of Andromeda, detected a faint radio transient that shared the exact same interval band as the magnetic spike. Not similar, identical. In the field of resonance physics, rhythmic intervals can matter far more than raw loudness or power. Think of it like this. The volume of the signal was incredibly low, but its rhythm was mathematically exact. And in cosmic detection, especially across vast distances, rhythm wins every time. The data lays out a startlingly precise relationship. The magnetometer spike, the ringing of our magnetic field, lasted for 12 seconds. The underlying radio pattern detected from Andromeda's direction repeated every 3.7 seconds. That is a perfect mathematical ratio, an elegant precision across 2.5 million light-years of space. This kind of uncanny frequency matching doesn't just happen by accident. When the 2004 Magnetar event from within our own galaxy shook Earth's magnetic field, our instruments detected the exact 7.5-second rotation period of that dying star in the data. The pattern was so incredibly precise that scientists could literally hear the neutron star's heartbeat pulsing in our planet's magnetic field. Some researchers now believe we are seeing the exact same phenomenon here, but on an intergalactic scale. A cosmic clock from Andromeda ticking in perfect sync with a resonance mode in our magnetosphere. The timing window is what makes this so compelling. Both the radio signal and the magnetic spike appeared within a narrow 6-minute detection window. The faint radio burst hit our outer sensors first. The magnetic spike here on Earth followed exactly 2.3 minutes later. That is the precise time that light, or any electromagnetic signal, would need to travel from the outer edge of our magnetosphere down to the ground-based sensors that also caught it. So how does a signal like this survive a 2.5 million-year journey through the harsh environment of intergalactic space and still pack enough of a structured punch to physically move our magnetic field? The answer may lie in the cosmic infrastructure that connects galaxies. These intergalactic filaments
Vast streams of magnetized plasma create direct pathways between galaxies like ours and Andromeda. They can act like cosmic cables or waveguides that can carry coherent signals across millions of light-years without losing their all-important internal structure. The energy requirements at the source would still be staggering. We would be talking about events that release more power in seconds than our Sun produces in centuries. But Andromeda is a colossal galaxy, host to over 1 trillion stars. The statistical probability alone says these kind of extreme, powerful events should happen. But there is another factor: dark matter. Andromeda doesn't travel alone. It sits inside a massive, invisible halo of hot plasma and, theoretically, dark matter. This invisible atmosphere extends far beyond the galaxy's visible stars, stretching for nearly 500,000 light-years from its center. This plasma halo can shape how waves travel. It can act like a cosmic lens or an amplifier, focusing and directing energy pulses along specific pathways, perhaps channeling them directly into the cosmic filaments that point towards us. What survives best across these incredible distances are coherent, low-frequency modes. These waves can travel for millions of light-years without losing their internal timing, their rhythm. Think of ocean swells. A powerful storm in the middle of the Pacific creates huge waves. By the time they travel thousands of miles and reach a distant shore, they are gentle, rolling swells. The raw power is gone, but the rhythm of that original storm is still perfectly preserved. If a signal from Andromeda hits Earth's magnetosphere, that last gentle ripple can still make it twitch. So what could be powerful enough to generate such a signal? 3 primary candidate sources exist inside Andromeda. First, a hidden magnetar flare. Andromeda hosts an estimated 100 million neutron stars, most of them undetected. A massive flare from one would be powerful enough to be visible across the entire local group of galaxies. Second, microactivity near Andromeda's central black hole. Its core harbors a supermassive black hole 200 million times more massive than our Sun. It's currently dormant, but even small bursts of activity can generate brief, hard energy spikes with precise timing. And in resonance physics, timing beats raw strength. Third, and most exotically, dark matter-linked variability. The mysterious 3.5 kiloelectron-volt X-ray line, a faint glow detected from Andromeda, suggests unknown physics at work. Some theoretical models predict this line should show weak, periodic variations. These fluctuations could modulate plasma flows along the intergalactic filaments, creating carrier waves that propagate toward Earth. We have seen a distant star ring Earth's magnetic field before, and that precedent from 2004 changes everything. It proved undeniably that Earth's magnetosphere can detect and respond to precisely timed signals from deep space. The signal from the 2004 magnetar was weakened by its 50,000 light-year journey. The signal from Andromeda would be weaker still by a factor of thousands. But if it hit the right resonance frequency, our modern quantum-grade sensors would still see our magnetosphere respond. This discovery matters because our modern civilization depends on stable magnetic fields far more than most people realize. Navigation and timing systems, from GPS satellites to power grids, rely on precise magnetic measurements. Tiny induced currents from external magnetic fluctuations can stack with solar storm effects, potentially causing cascading power outages. For defense and aerospace sectors, the need to distinguish a natural magnetic anomaly from a hostile electronic warfare attack is critical. Our new global sensor network, amplified by AI, is showing us that the magnetic environment of our planet is far more complex and far more connected to the wider universe than we ever imagined. To prove or disprove this extraordinary claim, a clear roadmap exists for scientists. It requires correlating more magnetometer data across the globe, checking deep radio and X-ray archives for matching signals from Andromeda, and running powerful supercomputer simulations of how signals could propagate through cosmic filaments. But the real question isn't whether this happened once. The most profound question is whether it's happening regularly, and we are only just now, in the 21st century, finally developing the tools to notice. We may find that our solar system is not an isolated island, but an active participant in a galactic-scale electromagnetic network that we are only beginning to understand, a network that connects our planet to the broader cosmic web in ways we never imagined.